4.3 is about logarithmic functions, logarithms. I know most of you guys have seen logarithms in your life before, okay? I know some of you guys can think, oh, we can do all logarithms with a calculator or an online source. Don't. You need to understand how to do this manually, okay? So where did logarithms come from? Logarithms are actually made up things. They are artificial. They didn't pop up anything in natural life, okay? So where do they come from? It comes from this question. Let's answer several questions here. Now this is 4.2 exponential functions. A number raised to a variable is called exponential. And somebody set it into 5, and we are trying to figure out what x might be. So you're raising 5 to the power mysterious x, and it still becomes 5. What do you think that x is? Easy question. 1. Right? It can't be any other number. It has to be 1, because 5 to the first power is 1. I'll skip this one, go to the next one. What power of 5 makes 25? 5? A little too high. 5 to the 5th is 5, 5, 5, 5, 5. That's not 25. It has to be only 2 of them. 5 times 5 is 25. 2. I will skip this one, go to the next one. Which power of 5 is 125? You got the idea. It goes 1, 2, 3. Okay, now let's go back to the main question. Which power of 5 is 20? Is it 1? No. 1 is 5. Is it 2? No. So it has to be something between 1 and 2, because 20 is between 5 and 25. So I'm guessing it's a decimal number. But do you have any guess? What decimal? 1 point what? What? 1.5? All right, let's give it a shot. So you need a calculator at this point. 5 raised to the power 1.5, you said? Take a look. Nope, you're short. You need to get 20. This is 11.1. Let's do better. Let's raise this up. What do you want to try next? 8, 1.8. 1.8 is 18. You're almost there. About 95. No, too much. 1.9. Okay, almost. Okay, you can do this all day. Wait, what math people experience is that, look, I'm almost there. I need to just change that second digit. I got the first digit right, I think. About 88. No lower than that. 7. Yeah, I think I'm almost there. 6. No, I'm too small now, right now. Now I'm going to add more digits. 1. About 2. You see, I'm improving at this stage. I got the first 2 digits right now. I'm working on my 3rd digit. And I'm almost there, you see? So you try this all day, all weekend, all semester. You will never be able to, never ever be able to get 20, perfect 20 on the nose. Never. Trust me. It's a never-ending number. It should be 1.86, and then numbers coming up, following it, and you will never be able to still get 20. But we believe that number exists, right? It exists. There is a magic number. When I raise 5 to the power of that, it's going to make 20, but we can never pinpoint it. We can never find it exactly. So what do you think mathematicians did for this case? We don't have patience to write all these digits because it's never ending. So they just manufactured artificially a symbol for it, just like for pi. They were too tired to write this number, so they just manufactured a symbol for it, this symbol, and for E, 2.7 something, they manufactured labels for this. They made a label for each case they encounter such a case. They made a label. So what do you think they called it? From now on, there is such a number, but I can't find all the digits. They call it LOG. They call it logarithm. Log is the short for logarithm, okay? But they said, oh, okay, for this one I need also logarithm. Oh no, for not that one. This one is also never ending, right? Never ending. So we need a symbol for this. So can I use the same log for this one? No, you will confuse these two because they are the same now. So we have to discriminate these two. So what do you think they did? They put whatever base you see here coming up, they put it here. Well, this is also half 5. Now they are still the same. So we need to still discriminate these, right? So just taking this base wasn't enough. What do you think they take also? They took these numbers and said, put it here. Now they are different. These are different. They said, I can't pinpoint this number, but I can call it a label. This is how they labeled it. LOG. This number pops up from raising 5 into power and setting into equal to 20. So this is just kind of a short phase of saying all this, reading this all out loud can be done with 1, 2, 3, 4, 5, 6 characters. They just shorten it, saying that there is a number never ending which is raised to the power of 5 and it makes 20. All said here. That number cannot be written shortly, so we call it a name. It's log 20, log 5, base 5, 60. So whenever you end up with a never-ending number, you turn it into a log symbol if it comes from, that never-ending number comes from an exponential equation. Even this one, this is a terminating number. We have a symbol, this symbol for it, but you can still write this as an log. How do you think you're going to write this? It's log, what? You put the base here, and what do I do? Put next? 125. So again, whenever you see something like this in sentence, you need to change in mind. This is a number, never-ending number, maybe terminating. Sometimes it can be a whole number, but that number goes to the top of 5 and makes 125. That's what logarithms is. It's just a compact way of writing a long sentence question, exponential equation question, in short terms. Okay? Make sense? I want you to convert these 3 problems back to exponential equation and verify they are correct. Maybe they are not. Somebody says there is a number raised to the power of 7 and makes 49, and that number is 2. Verify it by converting this into exponential expression. Write the equation in exponential form, and this is how you convert. Again, I sometimes do this with geometric objects. I call this, for example, a box. This part is a box. I call this a circle. Base is circle, and I call this number inside logarithm a triangle. It's a matter of reordering these 3 geometric objects. Where does the box go? Look, where is y? Box goes to the top of the base, so I need to click red actually. Where did the box go? The guy on the other side, outside of logarithm, the term independent from logarithm, it's not inside the logarithm, outside the logarithm, goes to the top. Base of the logarithm goes to the base of the exponential. So this is my circle. And where did x go? X was captured inside logarithm, now it's free on the other side. So that's triangle, right? Box, circle, triangle turns into circle raised to the box equals triangle. If you want to memorize that ordering. But again, my recommendation is directly understand, change this to English. It says a number raised to power of 7 becomes 49, and that number is claimed to be 2. Let's see if it's right. Again, You take the base as the new base. Base is the base of the exponential. But the number inside logarithm goes to the other side of the equation. And this number goes to exponent. Again, the result goes to the exponent. Base is the base. The prisoner captured in logarithm is the new result. They are reordered. Can you see that reordering? Alright, who wants to do this one? Okay, who wants to do that one? I know this one is hard. Why? How about this one? Again, always start with the base. What is the base? Put it down. And set it into equal sign. Whoever was imprisoned by logarithm 1 goes to the other side, right? So there is only one number left. I used this up. I used that one up. There is only 0 left. Where does 0 go?
Exponent.
Exponent. And always validify whether you did right or wrong. Is 13 raised to the 0 power really 1? This is how you check you're right. Is it true? Raise 13 into 0 power. Is it 1? Yes, because any number raised to 0 power is always 1. Again, come back here. Is 7 squared really 49? Yeah, 7 times 7 is 49. Now, how do we do this one? What is the problem with this one? There is no, what? What? Walter? We don't have what?
Wait, did that be in decimal form so it's got a negative S above it? Never.
You may change this into decimal, but no, that's not the answer I'm expecting. What is missing here? We expect to see 3 objects, right? A base and a number inside logarithm and a number on the other side. I have a number on the other side. I have a number inside logarithm. What is missing? Base. Base is missing. So did I forget to put it down?
No, it's base of 10.
No, this is just a shortcut we made. If a base is missing, it's not actually missing because we drop the base 10. We skip writing it if it's 10. So if you don't see any base, feel free to make it 10 because it's 10. Alright? So this is actually base 10. Now please change this now. I know 10 goes to the base. This number goes to the other side. Where does minus 4 go? There is only one spot it can go. Where? Exponent of this thing, right? Agree? No, this is wrong. It goes to the exponent of the base here. Not there. Okay? Is 10 to the negative 4 really 1 over 10,000? Is it? This is a good review of fact. If you have any number raised to the power negative power, it's actually 1 over that base with opposite power, positive end. So you have here 10 raised to the negative 4. 4 is 1 over 10 to the 4th. But 10 to the 4th is 10 times 10 times 10, which is 10,000. 10 times 10 times 10 times 10 is 10,000. So yeah, this equation really makes sense. Okay? So our first 3 questions were kind of easy. This was 7. This is how you type in, by the way. Or how do I make that power with this option? Or you can do shift 6. It goes to the top. And to go to the ground again, you need to use right arrow key or just click on it and makes 49. Okay, so I will skip number 2 and 3. What we're gonna do next is backwards. We're gonna flip now exponential equations to logarithmic equations. Look, this is an exponential, right? Exponents everywhere, no logarithms. You're gonna make it back here. This is given in the questions. You're gonna make it back to logarithm. So this trick works both ways. Exponential to log or log to exponential. We did log to exponential, now we're doing back. Okay. I bet we're gonna first put an equal sign and create a logarithm. Which side you want to put logarithm? It doesn't matter. You can pick a side and put a logarithm. It doesn't matter. You can put to the right if you wish. Now you have 3 numbers, 5, 2, 25, and 3 spots to fill in. 3 spots to fill in. Three numbers, 3 spots. Go figure. What comes to the circle? Base. Always base. Base goes to the base. This is called base, okay? 5. Alright, you have 50-50 chance for circle and triangle. You're at this. 2 or 25. What comes here? Yeah, the free guy on the other side, the one which away from exponent, goes to prison, log, captures it, and 2 that was earlier captured in the power goes to the right. So that says log 5 of 25 equals 2. Alright, let's test. How do you write logarithm? You can choose this one or type it in directly, log. Doesn't matter. How do I make that base? You know how? I need to make base 5 now. Can I just type in 5? No, this is not gonna work. You need to send this to underscore here by doing this, okay? Or shift underscore also works, okay? This, or in keyboard shift underscore, that was 5. And to go up again, hit the arrow, right arrow key, and put 25 in there. Equals 2. That was right? Yeah. What? What's the number 5? Number 5. Let me help you with this logarithm sign first. Equals, fill in 3 spots. One third goes where? Here?
Yeah.
Hmm?
Yeah, the index of the log.
Index of the log. So I need to set it a little lower than here. 1/3. And what comes inside log?
243.
243 equals
-5.
How about this? Still there are 3 objects here, x, 3, and y. You just need to put them here. Logarithm of base what? X of y equals 3. Okay? Alright, we're starting the real problems now. Because you haven't found any logarithms yet. All you did was rearranging terms. What is the question here? Nobody gave us what this is equal to, and nobody is asking us to change to exponential. Does it say change to exponential? No, they say find it out. Simplify and get me a number here. So how do we work this? Trust me, it's the same way we worked earlier. Now, I don't know what this is, right? Why don't we call it something? Call a variable to it, x. Remember, you are looking for x. So this means find x. Find x and you're done. Alright? You're simplified then. If you can get that x. Alright, isn't this just like this question now? Or this or this? You have three objects. Look, 1, 2, 3. No, not that one, sorry. It just looks like this question now. You have three things, 1, 2, 3, with logarithm involved. Logarithm of 1, 2, 3 items. Logarithm of 1, 2, 3 items. Just we don't know what x is. It's okay, we can still work this out. I need to just change the exponential. I put 6 to the base. And x goes somewhere, 36 goes somewhere else. Where? X goes where? To the 6, power of 6. And 36 goes to the other side. Look, an equation you have no clue turned into one of your favorite equations. Guessing a number raised to the power of 6, and that makes 36. What number x can be? What power of 6 makes 36? 2. Congratulations, you just found your first logarithm. You found this is 2. By looking at this as an exponential expression, I'm figuring out x that way. Okay? How about here? First off, base is missing. If it's missing, the base is 10. So you have log base 10 of 1000 equals x here. All three present. Let's flip. Flip this. Who wants to do the flip? Yep. Base goes to the base, x goes to the top, 1000 goes to the other side. What power of 10, you multiply 10 that many times and becomes 1000? 3. All done. Right? Okay, for these questions you were lucky. Because you could guess a power of 10 to make 1000. For this question you were lucky as well, but eventually you will run out of luck. But let's enjoy while we can guess these answers. Alright? Now, it's a little bit harder, but still same procedure. Call this an x. Work this out. I'll give you 1 minute to figure this on your own. Same deal. Not many tricks. Any answers? Negative 2. Okay. I guess that's right. I just need to justify. Alright, base is 7. X goes to the top of it. And the number locked inside goes free to the other side. Now, what power of 7 makes 1 over 49 and none of the whole positive powers does that? Because first power is 7, second power is 49, third power is 300 something maybe, okay? But it's not 1 over 49, so I need to go negative powers. I know if 7 raised to the first negative power, it's 1 over 7 raised to the positive power. That's not it. Go try negative 2. And we notice that it's positive 2, reciprocal of 7 squared, which is 49, and voila, we got it. X is negative. So again, if you have reciprocal 1 over something, search for negative numbers, okay? Negative 2 is that. Alright, why don't you try next one? Oh, by the way, before next one, we need to introduce you natural log. By the way, you already know this. If the base is 10, we don't show that necessarily. We may skip writing this, but it's called common logarithm. That's why it's common, we skip writing it. Base 10 is called common logarithm, and we don't usually show that base. You already knew it. But maybe this is new. There is a natural logarithm called, if your logarithm has base as the number e. Again, what is the number e? It's a never-ending number. That's why they come up with a symbol e. It's about 2.7, blah, blah, blah. So this is roughly 2.7. So when you see this base, weird base, now we shortly call it 2 letters instead of log, 3 letters. We call it ln, and we pronounce it really ln of x. Some people call it the long way natural logarithm x, but not necessary. You can call it ln x. So what do you do when you see ln x? Just imagining on your mind that this is actually a logarithm with base e and prisoner x, whatever that x is. Make sense? So work these out, work these questions out, knowing that ln means logarithm base e. So you have actually here logarithm base e of a number e to the 9th. Find it out. Well, we don't know that, so I call it x. Guess what we are going to do next? We will flip this back to exponential. I changed this into exponential, but base goes to the base. Set it equal. X goes to the top of the base, right? And this number, entire number here, after the logarithm, goes to the right. Oh my god, look at this. What power of e makes e to the 9th? Oh, this is a no-brainer. 9. Can x be any other number like 8? Is e to the 8 equal to e to the 9? No. X has to be 9. Actually, this is a property. If you have 2 exponential expressions with the same base, you can actually wipe them off, and x falls to the ground, 9 falls to the ground, and they become equal. X equals 9. This thing was 9. Make sense? What do you think this one? Again, if you're confused by this, it's nothing but log base e. Log base e.
It's -3.
Perfect. -3. Why? Again, call this x if you wish. Flip this. E is the base, x goes to the top. Entire thing in the parentheses go to this. Now this is trickier than this, because we don't have just e on this side. The e's are on the bottom. So I need to rewrite this. By the fact I mentioned earlier, if you have a reciprocal of a power expression, I can write that power expression without a reciprocal, without 1, by doing what? How can I make this 1 go away? -3. Flip the sign. Flip the sign, 1 goes away. Okay? So it works backwards as well. We usually do this. We have a negative number, we flip it into power, but it goes back as well. If you don't want it in the denominator, you want to flip it back, you need to flip the sign to opposite. Now x is equal -3 here. do not compute these via calculator again, okay? Don't. I know you can do calculator quickly here. But what if I put here 9 million? Can you type in ln to the 9 million into your calculator and compute it? I doubt it, okay? But I can compute e to the 9 million, just x equal 9 million, right? Alright, let's take a look at the last one. This doesn't have ln. What does it have? It has base 10 now. Not e, base 10. So we will flip this as well. Follow x. It's nothing different than what we did previously. It's just 10 to the x equals, wow, this is tricky. How many zeros we have? 1, 2, 3, 4, 5. What power of 10 makes that small number? Isn't this 10 to the negative 6? How did you get that so fast? Well, my recommendation is change that decimal into fraction first. Isn't this 1 divided by 1 million? Right? Just count how many digits you have here. 1, 2, 3, 4, 5, 6 after the dot. Then add that many zeros after the 1. 1 over 1 million is that number. And then 1 million means 10 multiplied 6 times. Because if I multiply 10 3 times, it's 1,000. 4 times 10,000, 5 times 100,000, 6 times 1 million. 10 to the 6. And then flip this just like you did here. X equals negative 6. Right? Okay? Any questions? Looks like a long set of questions, 19 problems, but no. Each question should take not more than a minute if you know what you're doing, okay? But that's not the standard, of course. It may take longer if this is the first time you're seeing such things. Okay? Well, as you've seen that changing things that way, canceling it out, converting a logarithm to exponential takes a while. I said 1 minute. My question is, can I do this under 10 seconds? The answer is yes, if you are willing to memorize a couple of shortcuts. These are shortcuts. Absolutely nothing new you're learning here. It's just the shortcut of, instead of changing every time a logarithm to exponential, you may learn a couple of common logarithms and how quickly you can compute them, such as, no matter what base is, this is the important one, red area, this red, 1. 1 is like a magic number when it goes into any logarithm. If you see 1 under any logarithm, it always makes the logarithm 0. Why? Because when you make this into exponential, that 1 can only happen if the power is 0, because 10 to the 0, 5 to the 0, no matter what base raised to the power 0, makes only 1 if the power, that power is 0. Okay? So from now on, when I see a question asking logarithm of some weird base, but only 1 observed, 1 is the key thing here, and we call that logarithm 0. Here, you can do this question in 3 seconds now. What is the answer? 0. Oh, this is a pi 3.14, a weird base. Shouldn't we calculating this by converting into exponential? No. If you see 1, 1 is a 0 maker. It's going to make the answer 0. That's it. Okay? Let's learn more tricks, such as this one. If you see 2 and base and the number inside matching, the answer is always 1. okay? Such as example logarithm base 331. Logarithm of 5 is 1. How about this one? What's that? What? It's 1. How is this 1? Because what does ln mean? It's logarithm base e. Oh, look at this. It's a match. If they match, it's 1. Okay? So when you have these two matching, call it 1. Okay. One level up. One level up. They are matching, but the term inside has a power x. Guess what the answer is? It's that power x. Kinda this turning into 1. 1 is wiped off, and you have this x surviving, so it comes right here. Okay? Just think like that. Alright? So when you have these the same, the answer is x. Key thing, bases must match. We don't care what you have on the top, it's going to be the answer. Again, log base 22 is x. Log base EE is x. Log base 1010 is x. Always, no matter what I choose. Same thing, but flipped. Flipped case. Here, logarithm was first, exponential was coming up next. Here, exponential is first, logarithm is coming next, but the key thing is these bases match, they match, then they cancel, x falls out. It's the answer, okay? So when you have exponential and logarithm come together, they kinda cancel out each other. Whatever is not left out is the answer. X is staying, X is staying, they are the answers. Such as 7 log base 7x is x. How about this? What if this is 7 and log base 6x? Oh, can I cancel these and make it x? No, this is wrong. Because why? 6 and 7 doesn't match. They are different. So we cannot say it's 1. Only it works if these two are the same. Those two are the same. Now you can answer this one. Result? Good. Why? These are matching. Otherwise, you should have done this. You should check this out by x, and then change this as 5 to the x equals 5 to the 13. It's not too bad. It still takes under 30 seconds. X is 13. You can still get the same answer. But why would you waste time if you could do this, right? And get 13 in a second. Alright, simplify this by using one or more of these properties. Let me write what explicitly this means. ln means log with base e. Oh, what a coincidence. Another e is coming up with the weird stuff on the top. Right. No matter how wild looking this is, weird looking, right? It's just consider it x. It's just like x. You have two or more items here, but still it's one big chunk of exponent. These will cancel, and that exponent will be the only thing surviving here. So it is m squared plus 7. Okay? But very important, all these items must be on the exponent. You cannot do this ln e to the n squared, and then plus 7. If this plus 7 is on the ground, not on the exponent, you cannot solve this question the same way I did. Because 7 is independent from the power, it's not on the power. So e will not be enough to cancel that out. Alright, we cannot compute that thing. Is this clear? Which one did we use here? We used 3 because of the matching terms. It's not too bad, only 4 properties. Did you already memorize them? 1, matching bases, matching base with a power, and matching base but log and exponential flipped. Kind of similar, right? 4 things. Well, I lied, there are 3 more. But before that, we need to learn some graphics. And we will learn 3 more. 7 is the end, okay? 7 rules and you're done, okay? Well, let's finish this section by learning graphs of logarithmic functions. Okay, this is from section, which section? 4.2, the previous one. The last thing we learned before exam was this, right? Exponential functions. Their graphs are either going up to the right side or they are sliding, declining to the right, correct? When? If the number base of the exponent, exponential expression is more than 1, it's rising. It's declining if the base is a small number like 0.5 or 1/2. Domain is entire real line. So you can find out, you can insert any x into the equation and it will always compute a number. This bus never fails you. Every time you insert an x from any number you wish, you can always compute it. However, the range is computed by looking at y-axis, compress this to y-axis. Range is only the positive y values and not including 0. Because these curves never touch ground, so you never obtain 0 value. So you're always more than 0. I'm just reviewing this. This is from 4.2. Nothing new, right? Okay? Now, how is this related to current concept of logarithms? This is how. Exponential functions and logarithmic functions are inverse of each other. Inverse. That means 4.1. If you want to find the graph of an inverse of a function, what did we do in 4.1 to find the inverse graphs? I am already giving you this graph and ask you to sketch inverse of this graph. Do you just reflect it along x? What did we do in 4.1? Do you remember this line from 4.1? What is this line called? It's y equal x straight line. If you want inverse of this curve, for example, this particular one I'm pointing at, all you need to do is reflect it along this green dashed line. So reflection of this side, that side, this point, and that point, and this point will be here. This point will be going that way. Will be something like this. Oh my God, it's this one. Now I know what logarithm graph looks like because it's inverse of this thing, b to the x. So if you have a logarithm with large base, it starts almost at 0 all the way down, goes up slowly but forever up. However, if the base is small, like 0.5, 0.1, 1/3, small, your function starts up here, goes declining, declining forever to negative infinity. Eventually you will go unlimited down, okay? A few points to make. Domain of a logarithm is range of an exponential. What is the range of exponentials? 0 to infinity. That's why the domain is 0 to infinity. Look, it's never touching 0, going into infinity. Range is, however, entire y line. Why? Because domain of inverse exponential was that. So they flip. These two flip and become domain and range. It has a vertical asymptote at x equals 0. You never cross this, but you go very parallel to it. And I already mentioned the other two statements. Again, if b is large, you start deep down and go increasing. If b is small, you go huge and drop down the values to negative infinity. That's the summary of the graphs. We are going to make one graph, this one, and we'll be done, okay? And that's Monday. Unless you want to do a second part. Yeah, let's keep it for Monday. Anyway, this should be due.